Alright, let's start the last chapter of the year. Woohoo! Section 13.1, Sample Spaces and Probability. Alright, our lesson objectives: find sample spaces, find theoretical probabilities and experimental probabilities, and our essential question is, how can you list the possible outcomes in the sample space of an experiment? So hopefully all these images here are a good indication of what we're going to be practicing in our lesson today. Alright, so some key vocabulary: sample spaces. We have probability of an experiment, which is an action or trial that has varying results. We have our outcomes; those are the possible results in a probability experiment. Our event, which is a collection of one or more outcomes. And then our sample space, which is the set of all possible outcomes. So let's consider flipping a coin and rolling a dice, those two events, finding all the possible outcomes and listing our possible outcomes. So you could try a tree diagram. So some starting point. So if we flip the coin, there's only two options. It could be heads or tails. If we roll the dice, we have six options. So if we flip and get a heads first, then heads then a 1, a heads then a 2, and so on all the way to 6. Or we could flip and get tails and then roll a 1, tails then roll a 2, tails then roll a 3. So these are all of our possible combinations using a tree diagram. Or you can work it out another way, use H for heads, T for tails, and just make a list. H1, H2, H3, so on through T6. So the total possible outcomes is 12. Next, let's look at theoretical probability, which is the probability of an event occurring. It's the measure of the likelihood or chance that the event will occur. So there's no experiment, we don't know for sure, it's just theoretical. Probability is the number between 0 and 1, including 0 and the 1, and can be expressed in three forms: decimal, fraction, or percent. So if we're looking at a scale from 0 to 1, 0 being impossible and 1 being absolutely certain to occur, it's 0% to 100%. And then you have your different forms: fraction, decimal, and percent. So it's unlikely at 1/4, it's likely at 3/4, certain at 1, impossible at 0. And then we know theoretical probability is when the number of favorable outcomes compared to the total number of outcomes. So if all the outcomes are equally likely, then the event can be found using this formula. And then we have a certain notation for probability of an event, which we'll call A. It's written capital P parentheses A. So let's change our formula to be probability of an event equals the ratio of number of favorable outcomes to total number of outcomes. So you'll see this particular notation here forward. So this is what you're practicing. All right, let's find theoretical probability of a student taking a quiz, randomly guessing the answers to all 4 true-false questions. What's the probability of the student guessing exactly 2 correct answers? So first, set up your probability notation. Our event is exactly 2 correct answers. We know that the ratio is the favorable out of the total. Let's build a sample space. So your different combinations of number correct. We only have 4 possible. You could get 0 correct, 1 correct, 2 correct, all the way up to 4 correct. And then there's different positions where your correct and incorrect answer choices could be. You could have all incorrects, the first correct and then the rest incorrect, or the second correct and the rest incorrect, and so on. So create your entire sample space. And then comparing, we have 6 possible exactly 2 correct combinations. So 1, 2, 3, 4, 5, 6 out of 16 total. Always simplify your fractions, so 3/8. And then convert to decimal and percent. So we have a decimal 375 chance, which converts to 37.5% chance of getting exactly 2 correct. All right, some quick facts. The sum of the probabilities of all outcomes in a sample space is 1. If you know the probability of an event, then you can find the probability of the complement of the event. Complement of the event is all outcomes that are not in event A and is denoted by the capital A with the bar above it. This notation R with the bar above it reads as A bar. The probability of the complement of an event, the formula is probability of the complement, which is this notation, equals 1, which is 100%, minus the probability that event A occurs. All right, let's find the probability of the complements. When two six-sided dice are rolled, there are 36 possible outcomes as shown. Here's your sample space. So find the probability of each of these events. Let's find the sum that is not 6. So that means we want the complement. So we want 1 minus the probability that the sum is 6. And we have 6, so 1, 2, 3, 4, 5 possible out of 36, which simplifies 1 minus 5 out of 36 is 31 out of 36. And that becomes decimal 861, or approximately 86.1%. Next we have the sum is less than or equal to 9. So our complement would be that the sum is greater than 9. And it looks like we have 6 possible. So 1, 2, 3, 4, 5, 6 out of total 36. So we subtract that from 1, leaving us with 5 6 simplified, decimal 833, or 83.3%. All right, let's look at geometric probability, which is the probability found by calculating a ratio of two lengths, areas, or volumes. So let's practice. You throw a dart at the board shown. Your dart is equally likely to hit any point inside the square board. Are you more likely to get 10 points or 0 points? So let's start by determining the probability of the event of our dart hitting 10 points, which is the area of the smallest circle out of the entire board. So I need the area of the small circle, which is pi r squared, so pi times 3 squared divided by the whole board, which is 18 squared. 18 comes by our full radius, so 3, 3, 3, which is 9. And then double that, that's 18. So each side length of the square is 18, so 18 squared. So that all simplifies to pi over 36 fraction, which converts to decimal 0.73. So there's an 8.73% chance that the dart will land at 10 points. Now let's take a look at the probability that it lands in 0 points, which is going to be on the outside of the circles. So we want the area of the outside of the largest circle out of the entire board, so the entire board shaded in. So we'll take a look at the entire square, 18 squared minus pi minus 9 squared, all divided by 18 squared. And that simplifies down to 4 minus pi divided by 4, which converts to decimal 215, which converts to 21.5%. So it's more likely that you would get 0 points. All right, let's do probability and length. So the probability that a point K chosen at random being on segment CD is the ratio of the length of CD to the length of AB. So part out of whole. So if CD is equal to 3 and AB is equal to 10, what's the probability of the event that point K is on CD? So if we label on our diagram, set up your probability of the event occurring, it would be 3 out of 10 chance, or decimal 3, or 30% chance. So there's a decimal 3 or 30% chance that point K lies on segment CD. Now let's look at probability and area. So here we have J is a region containing region M. The probability that a point K is in region J, chosen at random, will fall in region M is the ratio of the area of region M compared to the region area of J. So again, part out of whole. All right, so let's look at the area of region J being 12 square feet and the area of region M being 5 square feet. Find the probability that point K is in region M. So we're comparing region M's area to region J's area. So that's a 5 in 12 chance of point K being in region M, which converts to decimal 42, which converts to 42%. So there's a 0.42 or 42% chance that point K lies in region M. All right, so find an experimental probability. Let's say each section of a spinner shown has the same area. Spinner was spun 20 times, so this is an actual experiment. This is not theoretical. These are different types of probability. So this is like us collecting data, spinning the spinner 20 times, and recording all of the results. So the results are shown here in this table. So for which color is the experimental probability of stopping on the color the same as the theoretical probability? So we're comparing the two probabilities to find the same. So we'll start with finding the probability that we spin and get a red. So if we spin and get a red, our results are, we have a 5 in 20 chance. The 20 comes from totaling up our number of times we spin total. So total is always your denominator. And we got 5 red. So we went 5 out of 20, give me all the forms. So 25% chance of probability red. For green, it's a 45% chance. It's a 9 in 20 chance. For a probability that it's blue is a 3 in 20, which is 15%. And for a probability that's yellow is 3 in 20, so 15%. So you have 25%, 45%, 15%, and 15%. So when we compare, the experimental probability of stopping on red is the same as the theoretical probability. And that's based on, there are 4 colors. So for it to stop on red, that's a 1 in 4 chance, which is 25%. If we were to do no experiment at all, we have a 25% theoretically to land on red. Based on our experiment, the probability of red came out to be 25%. So 25% being red matches and is equal and same in experimental and theoretical probability. All right, so in the United States, a survey was conducted of 2,184 adults ages 18 and over, and it was found that 1,328 of them have at least one pet. The types of pets these adults have are shown in the figure, and this is a bar graph. So there's 916 that appear to have a dog as a pet, and 677 cats. 677 adults have cats, 146 have fish, and 93 have birds. So what's the probability that a pet-owning adult chosen at random has a dog? So let's start by identifying the event. We want the probability that a pet-owning adult has a dog. So that means our outcome, favorable outcome, is the number of adults who have a dog out of the number of pet-owning adults, so our total. And that's 916 out of 1,328. Simplify your fraction always, so 229 adults have a dog out of 332. That converts to decimal 69, which converts to 69%. So the probability that a pet-owning adult chosen at random has a dog is about decimal 69 or 69%. All right, so this is just our start to probability in the new unit. Bring clarifying questions and get ready to practice your probability skills in class. See you then.